Alright, so the last video talked about sort of the basics with an AC circuit. And so we know with an AC circuit what I'm going to have is I'm going to have a sinusoidal voltage source that's going to drive a sinusoidal current. And so now what we're going to do is we're going to come back and talk about, so what happens when you start putting our circuit elements, resistors, capacitors, inductors, into an AC circuit. So the first thing we really need to do is define what's known as the impedance. And one way to talk about the impedance, it's just the ratio of the voltage to the current. So when we talk about capital Z, that's the impedance. And that's just take the voltage, divide by the current, that's what the impedance value is going to be. The more important idea about the impedance is that it's a measure of basically what's the opposition to the current present within a circuit. So as you have your AC circuit is driving current back and forth across your circuit elements, the impedance is effectively measuring what the opposition to that current is. There are two types of impedance, or there are two sort of components that are going to end up factoring into the overall impedance within the circuit. One of them is the resistance, the other one is the reactance. And so the resistance is what you get when a resistor impedes current. The reactance is what you get when either a capacitor or an inductor impedes current. And so we'll talk about fundamentally all three of these things, impedance, resistance, reactance. They're all measured in ohms. Their units are all the same. But there are some subtle differences in terms of what they're trying to explain. So let's start with the one we already know. So resistance. And we said resistance is basically the opposition to the passage of current through a resistor. So if you try and run current through some conductor, there will be some resistance, some opposition to that. Essentially, that opposition comes from the fact that you've got, think of it as just friction as your electrons bang into each other trying to move through the conductor. And again, this is effectively just Ohm's law, right? We say, oh, it's V equals IR, where we've just rearranged it for the value of the resistance. So what happens when a resistor impedes current within an AC circuit? There's a handful of things. So one is, it doesn't depend on the frequency at which the voltage source is running. So we know we have a sinusoidal voltage source. That voltage source is running at a certain frequency. A resistor doesn't care about that frequency. So resistance doesn't depend on what frequency. You run it at a high frequency, you run it at a low frequency, resistance isn't going to change. Second thing is, the voltage and the current are in phase. One of the things that we'll see as we go through and talk about these various concepts is that there are going to be situations where the voltage and current are out of phase, but not across a resistor. As it runs through a resistor, the voltage and the current are in phase. And then the last one is that a resistor causes the loss of power. It dissipates energy, right? So these are sort of the basics when we have a resistor in an AC circuit. Reactance, again, it's a very similar concept, but it's an opposition of a circuit element to the change in the current or the voltage in that element. So effectively what this is it's an inertia that's associated with the motion of electrons. So the symbol we'll use for reactance is a capital X. And again, the reactance is it's still just the ratio of the voltage to the current. It just happens to be the ratio of the voltage to the current for either a capacitor or an inductor. So electric fields, which you set up in a capacitor, they resist changes in the voltage across the capacitor. Magnetic fields, which you have with an inductor, they resist changes in the current through an inductor. So basically the reactance is measuring the resistance to change in the field that you've set up within either of those two circuit elements. So when you have a capacitor or an inductor that's impeding the current, again, there's a handful of things that we can sort of broadly characterize. One is, now it will depend on the frequency. So whether you're running at high frequency or low frequency will change the reactance. across either the capacitor or the inductor. The voltage and current are going to be 90 degrees out of phase, and we'll come back in a minute and see exactly in which case the current leads the voltage and in which case the voltage leads the current. But the important thing is that when we're talking about the reactance, and so we're talking about the current and voltage across either a capacitor or an inductor, those two quantities, the voltage and the current, are out of phase with each other by 90 degrees. And then lastly, reactance doesn't dissipate. Energy doesn't disappear. You get all the energy back, because basically what reactance is telling you about is this resistance that changes because you have that energy stored in a field, and that field enables you to get that energy back. So you don't lose energy the way you do with resistance when you have a reactance. All right, so let's come back and look at our resistor first again. So we're going to basically set all these up by talking about a voltage source. We're going to have a sinusoidal voltage source. It's at some peak voltage. So this blue curve here is our voltage source. And then for a resistor, well, basically Ohm's law tells us that the current is just going to be the voltage divided by the resistance. So in this case, what I have is I have some current as a function of time that just has some peak value. Here's its peak value, and again it's also a sine omega t. So because there's not any sort of math, there's nothing more complicated than literally just dividing by the resistance here. I don't do anything to change the phase between these two curves, and so what that tells me is that the voltage and the resistance are in phase across a resistor. Now this diagram over here is known as a phasor diagram, and phasors are very similar to vectors. So basically this is what we're going to do is we're going to sort of plot out. I've got some voltage, I've got some current, and what I notice here is that the voltage and the current are in phase with each other. It means that they lie on top of each other. And now I can swing this around with my frequency omega, and that's a way to figure out what's going on within my circuit. Alright, so this is for a resistor. Let's look at a capacitor. So again, I'm going to start with my same sinusoidal voltage source, so Vp sine omega t, same blue curve. And then now to get the current, well, I know the current is just the derivative with respect to time of the charge that's sitting on my capacitor plates. That charge is equal to CV, and so now I really just need to take the derivative with respect to time of this voltage function. Well, when I do that, what I get is the C is just a constant, so that comes out. The peak voltage is just a constant, so that comes out. I'm taking the derivative with respect to time of sine omega t, that's just cosine omega t, and then when I use my chain rule to take the derivative of my phase in here, I know I get another omega out front. So I end up with this expression. I'm going to sort of reconvert this back to a sine curve, because now it becomes very explicit with this expression to see two things. One is it's very easy to see the phase difference. Right? So if my voltage is a sine curve, my current across the capacitor is a sine curve with the same phase plus a phase shift of pi over 2. And so what this tells me is that across my capacitor, the current leads the voltage by pi over 2, leads it by 90 degrees. And so that's what's designated here in my phasor diagram. Right now I've got the current in front of the voltage as this thing rotates counterclockwise. You can also see that within the curve, right? So what this means is that my current is basically starting at its peak value across the capacitor, even though the voltage across the capacitor is 0. And again, this makes sense because we've said that before you can get a voltage across your capacitor, you've got to start by getting charge on your plates. So if I've got an uncharged capacitor, there is no voltage across it, no potential difference between the plates. And so the first thing I've actually got to do is I've actually got to have a current So I can start to get charges on the plates. So this first chunk here is actually while my plates are charging. And then that'll happen up to the point where my current starts to reverse, and now they'll discharge. And then they'll charge again, and now they'll discharge again. So it makes sense that the current leads the voltage across the capacitor. Now the other thing that we'll see, we've said that when we're talking about a capacitor, we're talking about the reactance term. That's just going to be, again, the ratio of the voltage to the current. And if we think in terms of peak values, what you can see is I'm going to have the peak voltage divided by omega C times the peak voltage. The peak voltages will cancel, and so I'm left with the capacitive reactance is just 1 over omega C. So notice again we said that reactance does depend on the frequency with which you're running your circuit. There's that dependence right there. Alright, let's come back and do the same thing for an inductor. So again, for an inductor, we're going to start with our same sinusoidal voltage source. There's its curve. And so now, when I think about what's going on with an inductor, I know that the induced EMF across my inductor is equal to L times di dt. And so I basically just want to solve this for the current. And so when I rearrange this and undo the derivative by taking an integral, what I get is that, oh, the current is just going to be 1 over L times the integral of my voltage times dt. So this will be 1 over L times the integral of Vp sine omega t dt. And so when I do that integral, what I get is this minus sign, Vp over omega L cosine omega t. And again, I can sort of put this minus sign and the cosine, turn those back into a sine function by recognizing that the minus and the cosine will become a sine of omega t minus pi over 2. So again, this tells me that over an inductor, the voltage leads the current. So now instead of the current leading the voltage, this is just the opposite, where the voltage leads the current. And so again, that makes some sense to us because we said for an inductor is going to generate a back EMF, right? A large voltage that is trying to prevent the current from changing. So you'll have an EMF before your current is able to begin to change. So it makes sense that the voltage leads the current here. And again, it happens to lead by exactly 90 degrees. Again, if we think about what the reactance is going to be for an inductor, well, ratio of peak voltage to peak current, again, the peak voltage is going to cancel out, and I'm going to have 1 over this term. And so when I deal with that, what I end up with is that the inductive reactance happens to be just omega times L. So again, clearly a frequency dependence here. And so this is how I'm going to calculate the inductive reactance. Alright, so the inductive reactance, just like the capacitive reactance, just like the resistance, all of those are going to have units of ohms. And again, this is trying to tell me about how much my inductor is trying to oppose changes to the current. So if we think about sort of the way this plots out, and so here's our impedance term, and again we're just talking about sort of the impedance across either a capacitor, that's going to be this blue line, across an inductor, that's going to be this green line, or across a resistor, that's going to be this sort of brown line. And so first thing to notice is, well, across a resistor, again, it doesn't depend on frequency, it's just constant. But the inductive reactance and the capacitive reactance do depend. And so what happens is, for the capacitor, it has a very high reactance, so it's opposing changes. It greatly opposes changes at low frequencies. An inductor doesn't have any problem with changes at low frequencies. Instead, what an inductor does is it opposes changes at high frequencies. So when you have an AC circuit that oscillates with a very high frequency, the inductor is actually going to generate a large impedance to those changes. At high frequencies, the capacitor, again, its reactance has dropped off, so it's not impeding sort of the changes within the current flow much at all at high frequencies. And again, there's clearly this point where you go from the impedance being dominated by the capacitor to being dominated by the inductor, and that point happens to be right at a frequency that you can calculate as 1 over the square root of LC. And we notice that this happens to be exactly the same frequency that we talked about. So this is the natural frequency of some LC circuit. It's also the point at which you set your two reactances equal to each other. And so this obviously has a very special value in terms of AC circuits that we'll talk about in class. So at low frequencies, the impedance is dominated by the capacitor. At high frequencies, the impedance is dominated by the inductor. So what happens when we have all three elements within our circuit? Well, basically, if I've got all three elements within my circuit, then effectively what I'm going to do is I'm just going to piece them all together. And again, here's where our phasor diagram is going to be incredibly useful. So you'll notice that if we think about, well, the current, we're sort of going to set the positive x-axis as being what the voltage of the resistor will be. And then we know that across an inductor that's going to lead, the voltage will lead the current. Capacitor, it's going to lag the current. And so what we can do is we can basically calculate the impedance by just thinking in terms of what's going on with these vectors. So if I add these two, well, these two have y components, this doesn't have y components, so I get my net y component by just taking the sum of those. It's just going to be the voltage across the inductor minus the voltage across the capacitor. And so what I'm left with then is a simple two vectors, one in the x, one in the y, and so I know that adding those up is going to give me the voltage of my source. And so what this is telling me is that the voltage of my source will need to run with some phase shift relative to the current in order to keep everything working within the circuit. And so I can calculate the impedance by basically just saying, oh, well, this was the impedance in the x direction here, due to the resistor, plus the impedance due to the reactances of my inductor and capacitor. And again, since this is x and this is y, I'm just taking x component squared plus y component squared, taking the square root. To get the direction, or really in this case happens to be the amount of this phase shift, we use the same way we would think about the direction of a vector. So I'm taking my y component over my x component and then taking the inverse tangent. So this will let us figure out the impedance and then the phase shift between the current and the voltage when we have an AC circuit that has all three elements, a capacitor, a resistor, and an inductor. If we only have two elements, then obviously one of these, something here is 0, and again that's going to make it easy to figure out what's going on with the impedance and what's going on with the phase shift. But here's sort of our most general version for dealing with how things are running within an AC circuit.